Alrighty, these are the notes on section 6 of chapter 3. It's on introducing limits. And so what a limit is if you have your sequence a sub n as it goes from 1 all the way up to infinity, it's whatever it's going to be at infinity. So we'll say this equals the limit as n goes to infinity of a sub n, which we'll just call L for limit of a sub n. So this just means as n gets arbitrarily large, what does a sub n equal? And so first example would be limit as x approaches infinity of x over x plus 1. So we could try out the first two terms. We could say 1 over 1 plus 1 equals 1/2. 10 over 10 plus 1 equals 10/11. 50 for 50 plus 1 equals 50 over 51. As you can see, it's getting closer and closer to 1. And so we can say the limit equals 1. And another way we can show this is if we graph this out, so 2, 3, 4. If we graph this out at 0, we have 0 here. At x equals 1, we have 1/2. At x equals 2, we have 2/3. X equals 3, we have 3/4. And so on. And you'll notice we're approaching this horizontal asymptote at y equals 1, which indicates to us that x is going to keep getting closer and closer to 1, but never actually reach it. So that's one way we can determine the limit. Another way, which I'll show with more messy looking over. Look, if at first glance you really have no clue what this is going to be, you can plug 1, 2, 3, 4 in, and you'll probably start tending to something eventually. But let's be honest, no one actually wants to do this. They're looking for a relatively easy method. So what you can do is you can take this, and since we can multiply the top and the bottom of a fraction and keep the same, we can multiply by x to the -3 over x to the -3, and this will still equal the same exact thing. So what we'll be then left with is 1 minus 7 over x squared plus 9 over x cubed divided by 4 plus 10 over x. And so you're looking at this like, okay, it's still really messy looking. However, there is one more idea has to be introduced, and that is any constant over x for the limit of x approaching infinity, this will always equal 0, because no constant is going to be able to be anything compared to infinity, because it's going to end up between points 0, 0, 0, 0. And so we can just call that 0. And so we're looking for all things with x on the denominator, not on the numerator. So it'd be right here, we can get rid of this, get rid of this, get rid of this. That leaves us 1 over 4, and take the limit at approaching infinity. Well, x isn't actually affecting these, which means 1 over 4 should be our final answer for this. That's unfortunate. Give me a second to grab those. Alrighty. And if you want like a more just quick and dirty method, we'll just use x6 minus 7 x squared over 9x to the 6th minus 15x. What we can see is that anything with x to the 6th is going to grow so much faster than anything with anything less than x to the 6th. So anything else will, as we approach infinity, become less and less important, and so their importance will tend to 0. So anything that doesn't have the x to the 6th, since that's our largest growing thing, you can just get rid of it. We don't care about it. And so then, if we get rid of those, we are left with x over 6, x to the 6 divided by 9x to the 6, those cancel, we're left with 1 over 9. So, and also we could see x to the 9 plus 15x squared minus 7 all over 15x to the 7 plus 19x to the 6. What we can see is we can do this 2 ways. I'll write this smaller. Also, I don't think the values will be the same, but 9 plus 5x squared plus 7 over x to the 7 is 15x to the 7 minus 20x to the 6. What we can do is see x to the 7th is our largest x value in the denominator, so we can multiply by x to the negative 7th, and then we're left with x squared plus 5 over x to the 5th plus 7 over x to the 7th, or 15 minus 20 over x, and this will tend to 0, so we get rid of it. This will tend to 0, so we get rid of it. This will tend to 0, so we get rid of it. You're just left with x squared over 15. Well, if you think about it, x squared, if you plug in 100 for x squared, we're already going to get like 10,000 over 15, and that's just at 100. So imagine we put in 10 to the 100, and we have 10 to the 200 over 15. So it's very clear to see that this is going to go out to infinity. And so now that I've gone through those few examples, I'm going to introduce 3 formal terms. Convergence. This is when the limit approaches a value. So an example would be limit as x goes to infinity of x over 2x. This is going to converge to 1/2. Divergence. This could be like x squared over 19. This is always going to go to infinity. And then there's divergence by by oscillation. We have not covered this yet in the video. And so an example would be sine of x. It's always just going up and down and up and down. It's not getting any bigger, it's not getting smaller on average. It's just staying right around this value. So if you take the limit as it goes to infinity, where along its curve is it? We can't be completely sure where it's going to end up, so we say it's divergent by oscillation, which means we cannot calculate exactly what its limit is. Another example would be taking -1 to the x. It's going to go like boop, 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 boop. And so we don't know whether taking an odd value or an even value, so we don't know which one of these we're going to take, and since they're always staying at this 1 or -1, we have no way to determine what the limit actually is. And that should be it for the 3-6 notes. Bye.